Now have a look at page 10 of your electric field worksheet. Or maybe it should be 55. Just give me a moment. Okay, now, just have a look at page 10 first. We start with something easy first. Okay, have a look at page 10 of your electric field worksheet. This is June 16 P41. So give me some time to open it. June 16 P41. Question 6. This one requires you to draw some sort of graph. So maybe June 16 P41 question 6. How come I don't have it? Okay, yeah. Right. So if you look at page 10, this is June 16 P41. For this particular part, they mentioned to you that you have a solid metal sphere of radius big R isolated in space. The sphere is positively charged so that the electric potential as its surface is Vs. The electric field strength as its surface is Es. On the axis of figure 6.1 below, show the variation of the electric potential with distance x from the center of the sphere for values of x equals to 0 to 3R. Okay, so for your case here, if you consider your question, they say that you have a solid metal sphere of radius R. Okay, the most important thing to note is that this one is actually a sphere. Okay, so they mentioned to you that your surface of your sphere has an electric potential of Vs. Okay, so what they want you to find out now is the variation of your electric potential with distance x from the center of the sphere. So meaning to say right now, if this one is the center of your sphere, if you increase distance x from the center of the sphere, what would be the potential at this point, at this point? That's what they want to find out. How does it vary? Okay, so in your case, to find out what is the variation of the electric potential with distance, you would have to use back this particular equation where you say that V is equals to 1 over 4 pi epsilon naught Q over R. Okay, now one thing I did not mention to you just now is that this equation is only for point charges. Okay, now in the case where you have a sphere right now, this one is not an issue because I mentioned to you before that a sphere is actually identical to a point charge when you look at the electric field themselves, when you look at the electric field lines. Okay, so I can actually use this equation for the sphere, no issues here. Now from there, you can actually see this. If Q is constant, this tells me that potential is actually inversely proportional to R. Okay, so let's consider for the case outside the sphere. When you consider for the case outside the sphere, since potential is inversely proportional to R, or in my case, I think I better change it to follow what the question says. Rather than saying R, maybe I should just say it as X. Okay, in order not to cause you confusion. Distance X. Okay, so outside the sphere, your potential is actually inversely proportional to X. Okay, because the question uses X, all right? X here is the separation between your two charges. In your case, your first charge is the main charge. Your second charge is the test charge that you place inside the field. Okay, so X here is the separation between the charges. R is also the separation of the charges from before. They're exactly the same variable. Okay, so from here, what you want to do is this. You want to find out a few points of interest. When X was equals to R, the question mentioned to you that the radius of your sphere is big R. Okay, so when X is R, your potential is Vs. What about the case where your x is equals to 2r? Your potential would likewise be 0.5 Vs. Because here, your x has increased by 2 times, your potential must decrease by 2 times. You divide by 2. This one is compared with respect to the first case. Your x has increased 2 times, your V must decrease by 2 times. Then if you say that your x is equals to 3r now, your potential should rightly be 0.33 Vs. Because here, your x has increased by 3 times, so your potential must decrease by 3 times. Again, it's compared with respect to the first case. If you divide Vs by 3, you're going to get 0.33 Vs. So these are the 3 points of interest for you. Okay, which should be indicated here, here, and here. Then after that, you will need to join those lines together. All right. But you see here, you really only consider outside the sphere. You go from R to 3R. This is outside the sphere. What about inside the sphere right now? Because the question wants you to draw from 0 to 3R, not from R to 3R. They want 0 included also. So how would the potential inside your sphere actually look like? Okay, so this one you will actually have to refer back to the electric field notes, page, which page? Let me just find out which page is it. It should be page 15, okay? Just have a look at page 15 of your electric field notes. Last week, I explained to you why is it that for a uniform sphere, a charged uniform sphere, the electric field strength inside the charged uniform sphere will be 0. That one I explained to you already. Now, there is another thing that you also will need to know. That one being that when you're talking about inside a sphere, the electric potential would always be constant. Okay, so the reason for that is because of something like this. Okay, just now I told you that electric potential energy, just now I mentioned this, that change in your electric potential energy is actually equals to Q times delta V, right? Q times your potential difference. This one sometimes is also known as potential difference. Okay, the difference in potential between 2 points. Okay, so change in electric potential energy is equals to Q times delta V. All right, but at the same time, change in electric potential energy is equals to work done, isn't it? So I could say this. Work done is actually Q times delta V. Okay, so if you're talking about inside the sphere, earlier inside the sphere, I mentioned to you that your electric force will be 0 because your charge no longer moves. It's because from electric force being 0 that you eventually concluded that E is 0, right? So because your electric force is 0, inside your charge sphere, you could also deduce that electric potential will be constant. Okay, so why is this so? Is something like this. When you're inside the sphere, your electric force is 0. You actually have no capacity to do work. Because for work to be done, you must have force times distance move. In the first place, your charge don't move. And in the second place, your force is also non-existent anymore. So obviously your work done will be 0, right? So because your electric force is 0, you have no capacity to do work. Okay? Work done is actually 0. Okay? Then when you look at the original equation here at the top, if work done is 0, doesn't this mean that your potential difference will be equals to 0? So because delta V is difference in potential between 2 points If delta V is 0, that means no difference in potential. Therefore, potential is constant. Okay? If your potential difference is 0, that means potential never change at all. Your potential will remain constant. Okay? If you want to draw a graph of potential versus distance, it should just rightly be a straight horizontal line indicating constant potential. Okay? So the explanation why potential is constant is actually written in the notes here. I mentioned that inside a charged uniform sphere, there's no electric force. When electric force is 0, no work is done. And because work done is Q times delta V, when work done is 0, the change in potential is also 0. Therefore, potential remains constant here. Okay. Now, in terms of explaining whether potential is constant, it does not come out inside your past year questions. They do not ask you to explain why potential is constant, but your past year will ask you to explain why electric field strength is 0 inside the sphere. Okay, just so you know. Okay, so back to the question itself. You have actually drawn the part outside the sphere indicated by the red line here. So for the part inside the sphere, you really just need to draw a straight horizontal line that is not 0. You just need to draw a constant potential here like this. Okay, this one would be your complete diagram. Okay, just make sure that inside the sphere, you indicate that potential is constant. Okay, then after that, you'll be all right. This one is because V is inversely proportional to X. Okay, so that's how you get this graph shape. Then after that, you move on to part B. Part B is asking you to do this. On the axis of figure 6.2, show the variation of your electric field strength with distance x from the center of the sphere for 0 to 3R. They're asking you to do something similar again, but for field strength. So this one, I will rub off and explain the electric field strength first. For you, just give me a moment. Okay, now for electric field strength, you again need to refer to the equation for electric field strength where E is equals to 1 over 4 pi epsilon naught QQ over, not QQ, Q over R squared, all right? Q over R squared. So here, if Q is constant, this obviously means that E is inversely proportional to R squared, all right? So for your current case, you again have the same charge sphere where they tell you that the electric field strength at the surface of the sphere is actually ES. So they want you to draw the variation of your electric field strength with distance x from the center of the sphere in the graph below. Okay, so here, same thing, you can actually mention this. Oh yeah, one thing I did not mention here just now was inside the sphere, potential remains constant. Okay, this is for the first part of your question. Now, for the second part of your question, same thing, I need to write something similar. Outside the sphere, your E is inversely proportional to X. When X is equals to R, your field strength is actually ES. When X is equals to 2R, your E is actually 0.25 ES. The reason is because right now, your X increased 2 times, your E must reduce 4 times. Because your E is proportional to your separation square. Okay. E is proportional to your separation square. I overlooked this. This one I shouldn't write it as R. I should have written it as X. Following what the question wanted. Okay, so if your x increased by 2 times, your e must reduce by 4 times. The reason why is squared is because there's a square term here. Okay, so that's why you need to divide by 4 times when compared to the first set of values. Then after that, when your x is equals to 3r, your e would be 0.11 es. Because here, x increased 3 times, your e must reduce by 9 times. Again, this is compared with respect to your first value here. Okay, so when you want to plot your graph, you get this point, and this point. This is again for outside the sphere. All right. Now for the case inside the sphere, this one we've already gone through it in the example from last week. This one I'll probably just write it in past some comment here. Number 2, inside the sphere, field strength is 0. Okay. So when field strength is 0, it's just this line here. You join out with the remainder of your other lines, you will get something like this. Okay. This one is your field strength versus distance graph. Okay. So that should be it for this. Let me just write something here. This one is inside sphere. So field strength equals to 0 inside the sphere. Okay, so this question is all right. This is actually November 19 P42. Define what is meant by electric potential at a point. Electric potential from the definition inside your notes is actually work done per unit positive charge to bring a small test charge from infinity to a point inside the electric field. Okay, so you say work done to bring a small test charge from infinity to a point in the electric field, that's 1 point. But if you specifically mention per unit positive charge, that is where the other point comes from. All right, you must always make mention of per unit positive charge. Now for part B, in an alpha particle scattering experiment, the alpha particles are directed towards a thin film of gold as illustrated in the figure below. The apparatus is in a vacuum and the gold 197 or 19779 nuclei in the film may be considered to be fixed point charges. Okay, so they consider these nuclei to be point charges. So they mentioned also that the alpha particles emitted from the source each have an energy of 4.8 mega eV. So calculate out the initial kinetic energy in joules of an alpha particle emitted from the source. So before this, in particle physics, I would have mentioned to you that 1 eV is actually 1.6 times 10 power minus 19 joules. This is the conversion from eV to joules that you will use. So when you see this MeV here, this M here is actually mega, is a prefix mega 10 power 6. So when you want to change from 4.8 mega eV, you just need to remember to multiply with 10.6 followed by 1.6 times 10 power minus 19, giving you the kinetic energy of 7.68 times 10 power minus 13 joules. Okay, so this is pretty straightforward. Okay, now the other part is where you need to think quite a fair bit. Now for this other part of the question, they are asking you the distance d of closest approach of an alpha particle to a gold nucleus. Okay, they want the distance of closest approach of an alpha particle to a gold nucleus. So let's just consider a simplified example. You have one alpha particle that is moving towards your gold nucleus. Let's just say your gold nucleus, the thin gold film here, you consider just one small particle inside the gold film. You consider one gold nucleus only, as mentioned by the question. So say you have one gold nucleus here, all right? Now, consider the charges of the alpha particle as well as your gold nucleus. Your alpha particle actually has a charge of plus 4e, is positively charged. Because alpha 42, let me just write it on the left-hand side here. Because the nuclear notation for alpha particle is alpha 42, so this would mean that the charge of an alpha particle is plus 2e. And then when you're talking about the gold nucleus, is aurum 19779, right? The charge of your gold nucleus, aurum, is actually plus 79 E. Okay, so both are actually considered to be positive charges. So this one you have plus 79 E. So both are actually positively charged. What do you suppose is the direction of the electric force acting on your alpha particle then? If they're both positive, that means you must have repulsion. So your alpha particle will actually experience some sort of electric force towards the left. But the direction of your motion is actually towards the right. Okay, so what would then happen is that your alpha particle would actually try to move towards the gold nucleus, but it will eventually get slowed down due to the repulsion until it stops. And then after that, it will turn back. Okay, so when you're trying to move from here to here, what you can say is that your alpha particle slows down to a stop due to repulsion. Okay, so you eventually slow down to a stop. Let's just say that it slows down to a stop here. This one will be considered as the distance of your closest approach. Okay, the distance near your closest approach from an alpha particle to a gold nucleus. This particular D that they're talking about refers to how close can your alpha particle come to the gold nucleus. How far is it from the gold nucleus will it ever reach? So your D here is actually really this particular part. Let me just see how I want to draw it out. Your D is actually here. This is your D. Okay, they want to find out how close can your alpha particle come to the gold nucleus if measured from the center of the gold nucleus itself. Okay, that is what the D here actually means. All right, so you consider a few things right now. Your V here is 0. That means your KE here is 0. And when you come close to the gold nucleus, you slow down to a stop. That would have meant that your KE would be 0 here. Okay, so your KE here is 0. Okay, now when your alpha particle is going towards the gold nucleus, it has a certain speed v, but that v we do not know, but instead we know what is the kinetic energy. The kinetic energy, we've already found it from the previous part of your question. That one is actually going to be 7.68 times 10 power minus 13. So it's 7.68 times 10 power minus 13 joules. This is the KE at the start. Okay, let me just write it a bit towards the left. Your KE here is 7.68 times 10 power minus 13 joules. Okay, it will eventually drop to 0. Then after that, if I'm interested to find out the EPE between these 2 points, let's just say right now, I'm interested in the EPE at distance D. My EPE here would really just be 1 over 4 pi epsilon naught Q over D. Okay, that one would be my potential energy there. Okay, so this is 4 pi epsilon naught Q over D. All right, but how about the potential energy at the start when my alpha particle is coming towards the gold nucleus? Now, you will have to assume this is coming from infinity. Assume alpha particle is coming from infinity. So your alpha particle is coming from infinity. Just now I mentioned to you at infinity, your EPE should rightly be 0. Okay. So what you're really interested now is the energies at these 2 points in terms of their KE as well as their EPE. Okay, so if in the first place, you know that your alpha particle was slowing down to a stop due to repulsion, this is what you can probably say. Because you're slowing down, your KE is dropping. But according to conservation of energy, if your KE is dropping, obviously your EPE should be increasing. Okay, so from here, you could probably work out some sort of equation where you say that change in your KE, specifically the drop in your KE, is equals to the increase in your EPE. Okay. From there, you try to expand out your equation further. Now, one thing that I probably would have mentioned to you guys in the AS part for work energy power, for energy changes, always take the higher value minus the lower value. Okay, always just take the higher value minus of the lower value. So when it comes to the change in KE right now, the drop in KE, the higher value is actually this one. The lower value is actually the 0 there. Okay, so your equation thus becomes something like this. 7.66 times 10 power minus 13 minus 0. Okay, and then when it comes to the change in your EPE, you again would need to take the higher value minus the lower value. So your higher value is this one. The lower value is the 0 here. So it becomes 1 over 4 pi epsilon naught QQ over D minus 0. Oh yeah, I did a mistake here. The EPE here is not Q over D. It's QQ over D. Sorry, my mistake. Q over D is potential. EPE is QQ over D. 1 over 4 pi epsilon naught QQ over D. Okay, so this is the energy equation expanded out. From there, you just really need to sum in the values. All right, the remaining values. 1 over 4 pi epsilon naught is 8.99 times 10 power minus 10 power 9. You can get it from the second page of your exam paper. It's from your data sheet. Now, the QQ here, the big Q here is the charge of your gold nucleus. It is 79e. So it's 79 times 1.6 times 10 power minus 19. The small q here can be considered as your test charge is your alpha particle. So alpha particle, the charge is 2e, so it's 2 times 10, 2 times 10, 2 times 1.6 times 10 power minus 19. All right. Then from there, just find out what is D. Solve your equation and find out what is D. Your D would really just be 4.73 times 10 power minus 14 joules. Okay. So far, so good. All right. Then if you move on to part C, use your answer in B2, meaning to say use your answer here to comment on the possible diameter of a gold nucleus. So what do you suppose the diameter of your gold nucleus must be then, based on your answer in the previous part? So what is the diameter of your gold nucleus? Okay, maybe I should rewrite this as a different symbol. What is the diameter of your gold nucleus here, based on your conclusions from B2? Your diameter must be less than 10 power minus 14 meter. Okay? Because you see your distance of closest approach from the center of the gold nucleus was this value, right? The power of 10 is 10 power minus 14 meter. Your diameter must be less than this value. If it's larger than that, that would mean that your alpha particle would hit the gold nucleus directly, even before coming to a stop. So that one is usually not possible. Okay, your diameter must be less than that. That's why here the answer is diameter must be less than 10 power minus 14 meter. Okay, so that is for this particular question. Yeah, the marking scheme mentioned don't consider the 4.73, just consider the order of magnitude would be sufficient. All right, so that one is okay. You can just have a look at page 16. Actually, it's something from another different part of your chapter from last week. Okay, now here they mentioned to you two small solid metal spheres A and B have equal radii and are in a vacuum. The centers are 50 centimeter apart. Sphere A has a charge of 3 picocoulomb and sphere B has a charge of 12 picocoulomb. The range is as illustrated in the figure below. You have a point P that lies on the line joining the centers of the spheres and is a distance of 5 centimeter away from the center of sphere A. Now, suggest why the electric field strength in both spheres is 0. It's really asking you why is the electric field strength inside the sphere 0. So this one we went through it before in the notes. I think the answer that you can probably write is this one here. This one seems to be the one that is most consistent with what I explained inside the notes. You can just say that the charges in the metal sphere do not move. There is no resultant electric force from the charges, so no electric field. So no electric field strength if you wanted to like that, modify it later. So no electric field strength. No resultant electric force. So because E is equals to Fe over Q, if this one is 0, this one must therefore be 0. Okay? Initially, your charges do move, but because they tend to repel themselves as far away as possible to the surface of the sphere, after a while, they stop moving. Okay? It's from this point onwards that you consider. All right? So that's why we say the charges do not move anymore. Okay? But before this, they do move. All right? Now, for the answer that the Mackinson specifically gave for this question, they say in electric field, charges in conductor would move, but for the sphere, there's no longer movement or charge, so electric field is 0. It's actually kind of similar to what I wrote above, just that it's reworded differently, okay? But I would suggest maybe this one is the most consistent one with what you have in the notes now. If you use this, it should be applicable for this current question too, all right? Okay, so for part B, they want you to show that the electric field strength is 0 at point P. Explain your working, okay? So I'll just show you one method here. The way that the marking scheme answer this question is like this. You need to consider the resultant electric field strength at point P due to sphere A and sphere B individually. But how they did it was that they only consider the magnitude now. If you're talking about the field strength at point P for due to A alone, the field strength at point P due to A alone, if you use the equation 1 over 4 pi epsilon naught Q over R square, EA would be 1 over 4 pi epsilon naught QA over RA square. All right, so they just find the magnitude of the field strength due to A, where it is 3 times 10 power minus 12 divided by 4 pi times your RA square. Your RA is basically this one, the 5 centimeter here. Okay, this is your RA. All right, so you eventually get this answer, 10.79 Newton per Coulomb. Then after that, what you do is you consider the magnitude of the electric field strength due to B alone. Okay, you again use the equation, E equals to 1 over 4 pi epsilon naught Q over R square. So in your case, this one will be EB equals to 1 over 4 pi epsilon naught QB over RB square. Your RB is this one. Okay, this one would be your RB. You take 15 minus 5 centimeter, it will be 10 centimeter. So you use the equation there. EB equals to 12 times 10 power minus 12 divided by 4 pi divided by 8.85 times 10 power minus 12 times 10 centimeter square. Remember to change the meter. This is what you're going to get. Okay. You will get them both as same magnitude. That's correct. But how do you explain that the field strength is 0? That's where you have to kind of explain about the direction. You would have to say something like this. the fields due to the charge spheres are actually equal and opposite in direction. Therefore, your resulting electric field strength is 0. Okay, that's how the marking scheme answered this particular question. Now, if you have wanted to do it another different way, following what I usually do, you could probably just say this now. If you have a positive test charge here, the electric field strength due to sphere A alone will be EA in this direction. The electric field strength due to B will be in the opposite direction, like this. You already know that sphere A is positively charged. You also already know that sphere B is also positively charged. So your EA will be towards the right, your EB will be towards the left. Okay, so from there, if you want to answer it, you will just say that if you want to do it another different way, an alternative method, you first say that field strength due to A and B are in opposite directions. Therefore, EP is equals to EA plus negative EB. So from there, you just expand your equation. Sorry, QA over RA squared, right? You just expand your equation and prove that it's going to be 0. Okay, this is another different way of doing it. This one is more consistent with how I always find the resulting electric field strength. You can use this method too if you wanted to, but you need to specifically mention that the field strength due to A and B are in opposite directions. Okay, because I believe the marking scheme specifically wants to see this being mentioned. All right, so that's for this part. Okay, now C. C is what we want to do now. Calculate the electric potential at point P. Okay, so they want you to calculate the electric potential at point P. So if they want you to calculate the electric potential at point P, you consider the potentials caused by sphere A as well as the potentials caused by sphere B. So in your case, if you're talking about potential due to sphere A alone, it will just be VA. Okay, it will just be VA. But because V is 1 over 4 pi epsilon naught Q over R, whatever sign of your potential will tend to follow the sign of your main charge. Okay, so since your potential is, since your sphere A is positively charged, VA should be positive. Okay, then you consider the potential due to sphere B, you have potential due to B here, no direction to consider again. Because your sphere B is positively charged, VB obviously will be positively charged. Okay, so this is VA and VB. So that VP now is really just VA plus VB. There's no negative to consider. So this expanded out will give you 1 over 4 pi epsilon naught QA over RA plus 1 over 4 pi epsilon naught QB over RB. Okay. So this one will be your working that you have. Right? You can actually simplify it by bringing out or factorizing your constant. Okay. So here I mentioned VP is VA plus VB, 1 over 4 pi epsilon naught QA over RA plus QB over RB. This value of 1 over 4 pi epsilon naught is already given inside your data sheet again. So you can just sub it as one single value without doing any other calculations. Okay. So summing the values for QA, RA, QB, RB, you eventually get the potential as 1.62 volts. Okay. So that one is for this particular question. All right. So let me just clear off this diagram here. Okay, one last part to this question. Okay, I'll mention first that I'll probably run over the time by at least by about 5 minutes. If necessary, you have something to do and you need to leave first, you can do so. You can just refer back to the lesson recording later. Okay, so I just need to finish off this question because it's related to what we just did. Okay, now for part D, you have a silver 107 nucleus, argentum 10747 that has speed v when it's a long distance from point P. Okay, now when you see mention of something like this, a long distance from some point, this one already implies to you is from infinity. Okay, so when something is from infinity, your EPE you already know will be 0. Okay, so this one is just one thing to note first. Now, then after that, they ask you to use your answer in C. And your answer in C is the one where you found out that the potential is 1.62 volts. Calculate out the minimum value of speed V such that your nucleus can reach point P. Okay, you have a nucleus, a silver nucleus with a certain speed V coming from infinity towards point P. What's the minimum value of speed V such that the nucleus can reach point P? Okay, now to make sense of what this question is really talking about, what is this minimum speed that they're really saying? You consider that you originally have the two spheres, A and B here, A and B here. Both spheres were positively charged. Okay, and there was a certain point between the two spheres, particularly point P here. All right, that point P here, according to your question, you have a potential here of 1.62 volts. Okay, so here in your question D, they mentioned that you have some other nucleus, a silver nucleus that is going towards point P here, and it's coming from infinity. So say, for example, your silver nucleus is this yellow colored particle here that I will write. It's your argentum nucleus. It's coming towards your point P with a certain speed V. Okay, and it's coming from infinity. So it's coming from infinity. Your EPE here will be 0. Your KE here will be half mv squared. All right. So as it tries to approach your point P, what do you suppose will happen to your silver nucleus? You consider this. Your sphere A and sphere B are both positive. So what you can think of is that this whole region is really positive now. Your argentum nucleus is a nucleus, so it must be positively charged, okay? If it's a nucleus, it must be positively charged. So argentum, not aurum, sorry. Argentum 10747 would mean that your charge is plus 47E, your mass of your argentum nucleus is going to be 107U. Okay, this one you use later. But the thing that you just need to know is that your argentum nucleus has a charge, a positive charge of plus 47E. Okay, so your argentum nucleus has a charge of plus 47E. It itself is positively charged. It's approaching a region that is also positively charged. So when you're talking about the electric force that is acting on your nucleus, it's obviously going to be repulsive, isn't it? So you can kind of say that your electric force acting on your argentum nucleus is actually going to be in this direction. Let's just say, for example, away from point P. Okay, so if you're going towards point P, but your electric force is the other way, what does this tell you about your particle? What will happen to the particle? As you're going from here to here, you will slow down due to repulsion. Then your charged particle, your argentum nucleus will slow down to the repulsion. So this tells you that your KE would drop, and in return, your EPE would increase. Okay? So from there, you can actually say that whatever loss in KE that you have must therefore be the increase in your EPE. You will use this in order to solve the question to find out the minimum speed V. Okay, so just now I mentioned to you that your charged particle will slow down due to repulsion, right? So it will slow down until it reaches V equals to 0 here. This is where your KE would be equals to 0. Because you read the question, they want the minimum speed V such that the nucleus can reach point P. So when you see this phrase here, minimum speed V such that the nucleus can reach point P, it already tells you that the V must be 0 at point P. Because as your object moves from infinity towards point P, it's slowing down, isn't it? So you want the speed that is just enough for your particle to reach point P. So when it's just enough to reach point P, your speed must be 0 there. Okay? So that's why here I can say this. Your KE is 0 because your speed is 0 here. Alright? So that is for this. Okay, then if you wanted to do your question based on this equation, you could say that decrease in KE is equals to your increase in EPE. Your decrease in KE would just be half mv squared minus 0. You take this minus this. Okay? But when it comes to the change in your EPE, just now I mentioned to you that EPE at a point is QV, right? This one is at a point. When you're talking about change in EPE between 2 points, is Q delta V. Okay, this one is between 2 points. Okay, because the question asks you to use the answer in C, the one where you say potential is 1.62 volts, you generally will want to use this. Okay, so change in EPE between 2 points is Q times potential difference between the 2 points. The potential at point P, you already found it as 1.62 volts. Now, at infinity, where your silver nucleus came from, it is correct to say that your EPE is 0, but at the same time, it's also correct to say that your potential is also 0. Okay? So you make use of potential here rather than potential energy. So your EPE change is Q delta V. In your case, your delta V is really just 1.62 minus 0, giving you 1.62 volts. Okay, this is your delta V. Okay, then if you have that, you can now sub it inside this equation and solve your equation and solve your answer, and solve to find your answer. Let me just rewrite it here on the left hand side, because the one that I just wrote is, I think, a bit messy, not consistent with what I'm saying. This is half mv squared minus 0 is Q delta V. This one will just be half 107u V squared equals to 47e times delta V. Okay, so if you want to, you can probably start with this now. Okay, so you will just take half 107u, u is 1.66 times 10 power minus 27. U is your unified atomic mass times V squared equals to 47 times 1.6 times 10 power minus 19. E is your elementary charge times delta V, 1.62. Eventually, you'll be able to find out what is your V. Okay, your V is really just 1.17 times 10 power 4 meter per second. And that's how you got this answer here. All right. So that is for this particular question. It's kind of similar to the one that we just did before. It's also talking about something that is moving towards a positive charge. It slows down to a stop. Find out what's the distance or closest approach. And then this one is also something that is going towards one particular point. It's also slowing down to a stop, but this one, they want the minimal speed. Okay, let's just have a look at page 63 of your worksheet. All right, so we'll go through an easy example question first. So define electric potential at a point. This one we already went through it last week. It's work done per unit positive charge to bring a small test charge from infinity to a point inside the electric field. So just reproduce back the definition from the notes and you will be fine. Now, if you look at part B, there are 2 point charges A and B separated by a distance of 12 centimeters inside a vacuum as illustrated in the figure below. The charge A is 12 times 10 power minus 9 coulomb. You have a point P that lies on the line joining charges A and B. This is your point P here, and it's between charges A and charges B. And its distance from A is actually x. So here they mentioned that the variation with distance x of the electric potential B at point P is as shown here. So if they were to start measuring your x from the left-hand side from A, this graph below here shows you the variation of your electric potential with distance x. So from there, later on, if you look at the next part, they are asking you to use that figure to determine what is charge of B. Okay, they want to know what is charge B here in the first place. In your question, they really only told you that charge of A is this value here. Is going to be a positive value, okay? But they never did tell you what was the charge of B, okay? So here, you can kind of do something like this. If you're considering point A and say you are interested in testing that point, you would normally put a positive test charge there. So if you consider the individual effects due to each of the point charges A and B, you would have a potential due to A. Okay, you have a potential due to A. It has no associated direction because potential being a scalar has no direction. But because your charge A is positive, this one you already know is positive. Okay. Then after that, if you go on to consider the individual effects due to charge B, you would have VB here. But because charge B is unknown, you don't even know what's the sign of the charge. Let's just leave it as it is like this. Okay. So here, if you have wanted to find out what is your potentials at P itself, you could have just say BP is VA plus with VB. Okay. So this is what you are going to have. And then now you look at your graph that is below here. There's one particular point of interest for you. That point being this one. This point here is where VP is equals to 0. So that would have mean that VA equals VB. Sorry, that would have meant for you that in your case, VA plus VBE is equals to 0. So from here, you want to kind of sub out a few things. VA will be 1 over 4 pi epsilon naught QA over RA plus 1 over 4 pi epsilon naught QB over RB equals to 0. Because if you remember the equation for potential was 1 over 4 pi epsilon naught Q over R. So here you need to be careful about what is your RA and your RB. Your RA is your distance from charge A to the point that you're considering to point P. Your RA is actually X itself. Okay, this is your RA. And then after that, when you're talking about your RB would rightly just be this one. Okay, this is your RB. So here, if you want to look at your graph, you can actually straight away deduce what is your RA from here. Your RA is really this one here. This is your RA. And then your RB will be all the way to here. This one is your RB. Okay. So this one is exactly all the way to 12 centimeter, which is what the question stated there in the diagram. So this is a correct graph. They drew it all the way from one charge to another charge. Okay, so this is your corresponding RA and RB. You can actually just read it from your graph. is actually 4 centimeter and 8 centimeter respectively. Okay, so let me just kind of write it here. This one is 4 centimeter and 8 centimeter respectively. Giving you something like this, okay? So you just start everything in, try and simplify wherever you can. Eventually, you should get some final expression where you get this. Okay, just let me erase off everything. So now I told you that your V is 0 when X is 4 centimeter. That means VA equals to VB equals to VP equals to 0. Okay, this part here is actually VP lah, right? And it's equals to 0. So when you try to expand it out, you get this expression. Okay, so 1 over 4 pi epsilon naught QA over XA plus 1 over 4 pi epsilon naught QB over XB. Okay, yeah, here I use XA lah because I think I'm trying to follow the convention used inside the question because the question used X, so I use XA, XB here. But you wanted to use RA, RB is also fine. It doesn't matter. All right. So what is of interest to you is that the 1 over 4 pi epsilon naught will eventually cancel off. So your final expression would really just be QB over XB equals to negative QA over XA. All right. You know what is the value of QA, the distance XA, the distance XB. So finally, you can find out what is QB itself. All right. So eventually, your final value of QB, if you start everything in properly, is that you will get negative 4.0 times 10 power minus 9 coulomb. All right. So 1 mark for your equation being correctly stated, another mark for your magnitude being correct, and another mark for you actually identifying that is a negative charge. Okay. Yeah, and also don't forget your power of tens from your graph. This one, I believe, is right over here. No, wait. Your power of tens, there is no power of tens here to consider, but there is the centimeter to consider. Right? Because here you see your distances is in centimeter. Just remember to change it back to meter. That's why you get the 10 power minus 2 here. Okay, so this one is pretty straightforward. Then let me just erase it off. Let me just clear off everything. Okay, so then after that, you look at part 2. The change in electric potential when point P moves from position x 9 centimeter to position where x equals to 3 centimeter. Here, they really just want you to find out the change in electric potential when your P was shifting from 9 centimeter to 3 centimeter. Okay, so you look at your graph. If you're shifting from 9 centimeter, this one is actually your 9 centimeter mark. You're shifting from here to the 3 centimeter mark, which is right over here. Okay, you're shifting from here to here. Okay, this point here. So what the question wants you to find from there is the change in potential between those 2 points. It's probably better if I just draw a straight line like this. Okay, so what they want is the change in potential between these 2 points. Okay, so this is pretty straightforward to do. You just take with the higher value minus the lower value, meaning to say you take the positive value minus the negative value. Okay, so here you should be getting 2 minus negative 10. And then don't forget your power of 10, 10 power 2 here. You will eventually get your change of potential as 1200 volts. Okay, so this is pretty straightforward. Now, the last part here in C is telling you that you have an alpha particle that moves along the line joining point charges A and B in the figure previously. The alpha particle moves from the position x equals to 9 centimeter and just reaches the position where x is equals to 3 centimeter. Okay, now the part where they say just reaches the position 3 centimeter, this one should alert you that it is saying that your alpha particle actually comes to a stop so that V is equals to 0 here. Okay, so how do I actually know that it will just come to a stop? It's because I know that from 3 centimeter to 9 centimeter, the particle is slowing down. Okay, I know that from 3 centimeter, sorry, not 3 centimeter to 9 centimeter, it's the other way around. From 9 centimeter to 3 centimeter, when you're going from 9 to 3 centimeter, your particle is actually slowing down. You can actually deduce that from looking at the graph. If you see the diagram below here, which is actually a reproduction of the graph previously, 9 centimeter is right over here, where you have negative potential. 3 centimeter is over here, where you have positive potential. So if you are moving from here to here, 9 centimeter to 3 centimeter, notice that your EPE is actually increasing. If your EPE is increasing, this tells you that your KE by right should be decreasing according to conservation of energy. So I know now that if I had an alpha particle that is trying to move from here, I have an alpha particle that is trying to move from here to here, it will now slow down just by looking at the graph itself, because your KE is decreasing, so you are actually slowing down. So if you are slowing down, it will make sense that you could have a case where you just slow down to a stop somewhere. So the question here has actually made mention to you specifically when you reach 3 centimeter, your V is 0. Okay. So that's just one thing to note here. Okay. Now, then after that, the question wants you to find out what is the speed V. Use your answer in B2 above to find out the speed V of your alpha particle at the position where x is equals to 9 centimeter. So here they want you to find out what was the velocity V that you started off with at 9 centimeter, such that when you reach the 3 centimeter mark, it is 0 meter per second. Okay, so you again will rely on your conservation of energy equation, where you say that whatever increase in EPE you have is actually equal to the decrease in your KE. So in your case, what we learned last week was that if you are interested in finding out the changes in EPE of a part between 2 points, it's just Q times the potential difference between the 2 points itself. So here I can just say it's Q delta V, and the delta V actually will be using the value I found above here. That's the reason why the question asks you to use D2. Okay. And then as well, your KE will actually just be half mv squared minus 0. There's a 0 here because at the 3 centimeter mark, you are already at rest. The half mv squared here, the other term is actually at the start here. All right. So that being done, all you are just left with is just to substitute out your values. Because you're talking about alpha particle here, alpha 42, you should also know that your charge of your alpha particle is plus 2e, whereas the mass of your alpha particle is 4u. So here, this is your charge of your alpha particle, 2 times 1.6 times 10 power minus 19 times your potential difference, then equals to half times the mass of your alpha particle, 4 times 1.66 times 10 power minus 27, multiplying with your v squared. Eventually, you get this answer. Okay, so this is a very straightforward example. Okay, then I go through another straightforward example before I go through the very complicated one. There are two questions that are linked together that are very, very complicated. Okay, so here, if you're okay with that, then we move on to another simple question. Just have a look at page 7. Page 7, November 15, P43, which is this one. Okay, here the question mentions something like this. They say that you have a positively charged solid metal sphere that is isolated in space, is a point charge. Based on that statement alone, the electric field strength E is measured for different distances x from the center of the sphere, and the variation with x of the field strength E is as shown below. Now, suggest why for values of x less than 4 centimeter, the electric field strength is 0. So we've actually done a question similar to this last week. Okay, so before I go through the answer, let me just draw something here. You have a sphere, okay, whose radius is 4 centimeter. centimeter somewhere. Did they say that? No, they didn't say the radius is 4 centimeter. They just mentioned that your distance x is measured from the center of the sphere. If this is your center of your sphere, you measure x from the center of your sphere. So here, they are interested in the variation of your electric field strength with distance from E1 to E2 to E3. So the graph of field strength versus x that you have is this one here. Okay, so you are asked to explain why is it that for x less than 4 centimeter, which is right over here, your field strength is 0. Now, this part here where x is equals to 4 centimeter, you should already automatically know that this is actually inside the sphere. So whatever is on the other side, this one is actually outside the sphere. And the variation that you see here follows E equals to 1 over 4 pi epsilon naught Q over R square, such that E is inversely proportional to R square. But for the part where it is inside the sphere, this one E is equals to 0. I explained it to you last week already, or the lesson before that. So why is it that for values less than x equals to 4 centimeter, or for inside the sphere itself, your field strength is 0? So some of the answers you could use is that you could say that in your sphere, your charges in your metal no longer move. There is no longer any resultant electric force on the charges, so there is no electric field or electric field strength because here the question asks you to define electric field strength, right? So maybe you just write this. So it comes from this concept here where you say that it comes from this concept where you say that field strength is Fe over Q. The moment you do not have any electric force, this would tell you your E would be 0. Okay, so this is your standard answer when it comes to why field strength inside a sphere is 0. Number one, the charges in your metal don't move. Number two, there is no resultant electric force on the charges. Therefore, no electric field strength or no electric field. Okay, they kind of mean the same thing. So this part here is actually inside your notes under page 15. Okay, this is a detailed explanation. So back to the question at hand. Now, part B is the one that is a bit different than the rest of the questions that you've done so far. If you were to look a bit downwards to question part B. Okay, so let me just go back up here. If you look at question part B, you have a point charge of 8.5 times 10 power minus 9 coulomb that moves from a point x 7 centimeter to a point where x is 5 centimeter. Use the figure to estimate the change in electric potential energy of this point charge. Okay, so let me fill off everything here now. You have a specific charge of a certain value that you're trying to move from 7 centimeter to 5 centimeter. What is the change in electric potential energy at this point? So here, your 7 centimeter is right over here. This one is your 7 centimeter. And you want to move it to 5 centimeter. Right over here. Okay. So based on some of the examples we've done so far, because they say change in electric potential energy, the thing that might have come to your mind is that you probably want to find the charge times the change in electric potential. Now, if you look at your graph carefully now, this is not a graph of potential versus distance. This is a graph of electric field strength versus distance. Okay, is an entirely different graph. Because if let's say you had a graph of potential versus distance like this, it would have rightly just been something like this. If you had wanted to find the change in potential between 7 centimeter to 5 centimeter, you could have easily just found it from the difference in these two values between this point and this point. That is the normal standard way of doing it. But here your question gives you a different graph. It gives you an electric field strength versus distance graph. So how are you going to find the change in potential here? You cannot just simply say it must be related to the gradient or something like that. That one is not applicable here. So here you need to make use of some other equations that you have learned. You need to kind of modify and express it as another different equation. This one is actually not explained inside my notes. So this one is probably something you need to kind of write down. Now for electric field strength, you guys would have remembered that is 1 over 4 pi epsilon naught Q over R squared. Okay. Now, and also, you also know that potential is 1 over 4 pi epsilon naught Q over R, right? So, you will make use of these two equations and you will somehow combine them together. So, how does it work? You say something like this first. E is 1 over 4 pi epsilon naught Q over R squared. This is the same as you saying 1 over 4 pi epsilon naught Q over R times 1 over R. Okay, so notice that this expression here, 1 over 4 pi epsilon naught Q over R, is actually this one here. Okay, so therefore, you could have actually just said that electric field strength is also potential times 1 over R, such that potential is E times R. This one here will give you potential at a point. Same like the one above, but this one also gives you potential at a point. Okay, but in the context of your current question, you cannot use this one directly. You have to use a different form of it. So this one is the equation that you need to use. Okay, so this derivation here that tells you that potential is actually the field strength times the distance or the separation. This is actually not inside your notes. Okay, so maybe you need to write it somewhere. As far as I know, in your past year question, this is the only instance where you need to use this equation. The rest doesn't seem to need you to know this. Okay, so here, if you're moving from the 7 centimeter mark to the 5 centimeter mark, you could say that here your E1 is actually, sorry, your V1 here is going to be E1 times R1. And then if you go on to the 5 centimeter mark, it will be V2 equals to E2 R2. Okay, so you just need to read the graph, put in the values, and calculate it out. So you now look at your workings. I already say here for point charge, V is equals to EX. I use VR, ER. They are again interchangeable, up to you whether you want to use X or R. So the change in potential is actually V1 minus V2 is EX1 minus EX2. Get the values, substitute them in. Eventually, you will get 0.74 volts for the potential difference. From there, you can now work out your change in electric potential energy, which is just Q times the change in potential. The charge is already given as 8.5 times 10 power minus 9. Your potential difference has already been found on the left-hand side here. So just sub it in, you will get your answer as 6.29 times 10 power minus 9 joules. Okay, so pretty straightforward.